I'm Matt Swartley with Chariot Solutions, and I would like to introduce you to Sweety, Bertilla, a principal software engineer at Comcast, and Robert Farnum, a distinguished engineer and architect also at Comcast. Today, they are going to share their experiences with a lightweight messaging protocol called Message Queuing Telemetry Transport, or MQTT. So please welcome Sweety, Bertilla and Robert Farnum.
Hello, thanks for joining a talk on MQTT, a message standard for IoT. And my name is Sweety Bertilla. I work as a principal Android engineer and a tech lead for a client feature, which works in IoT, which uses MQTT a lot.
Hi, welcome. My name is Robert Farnum, distinguished engineer and architect with Comcast Cable and Connected Living, and working over the smart home vertical. Next slide. Excellent. So question, does your application make network calls? Most of the time, yes, that's what we do. We make network calls. But how do you make those calls? Typically, most people probably use HTTP, REST APIs, for example. But have you thought about MQTT and how it's different than HTTP? But what is MQTT? So let's discuss. So first of all, it stands for Message Queuing Telemetry Transport. Most people just really call it MQTT. It is a commonly used protocol for machine-to-machine and IoT, which is Internet of Things. It is a very lightweight messaging protocol, making it suitable for devices and mobile applications alike. At the heart, it supports a message paradigm pattern called publish, subscribe to exchange data between a client and a server. It's based on subscribing to topics. And so we'll talk about the hierarchy of strings used to create message topics and enable you to publish and subscribe to those topics. And then finally, MQTT communicates through a common message broker. All clients connect through this message broker. Next slide. A little history. It was created quite a while ago. Back in '99, gentleman from IBM, Andy Clark, and Aram Nipper from Eurotech invented the protocol. And it was invented for unreliable networks and satellite communications, which you can imagine back in the time was fairly unreliable. In 2011, it was actually donated to Eclipse PAHO as the PAHO project. 2013, it was adopted as an OASIS standard. And 3.1 was released in 2013. 3.1.1, which is the version actually we use, was ratified in 2016, which is fairly recent. But 5.0 finally supersedes 3.1.1 as of 2019. We look forward to being able to adopt that new standards. And finally, in 2016, it was also published as an ISO IEC standard. Next slide. So again, why? First of all, it is a lightweight messaging protocol. It's low on network bandwidth. It doesn't do a lot of intercommunication between the client and the server other than a keep alive to keep that connection, bidirectional connection open. It supports asynchronous messaging patterns, which is common with a pub-sub network paradigm. It supports 3 levels of QoS, 1, 2, and 3, which we'll discuss in depth. It allows clients to easily publish messages and subscribe to messages and receive those messages over topics. And finally, due to shorter messages and low network bandwidth, it can save battery life on devices that are battery powered. Next slide. So the protocol, guarantees high delivery through quality of service as compared to, for example, HTTP. It has a shorter specification in network headers than HTTP typically does. A lot of, for example, the header that we send every time for authorization in HTTP is sent once when we first initiate the connection for MQTT. The messages are usually smaller in size, lowering the bandwidth requirement and saving battery life as compared to using an HTTP-based protocol. And then finally, it is asynchronous in nature. So we publish messages, we're done, fire forget. We subscribe and receive messages when they're available on those topics. There's no longer a requirement to do long or short polling as we typically do with an HTTP protocol. Next slide. So what are the major entities involved in an MQTT network? There's two. There's messaging clients and there's the message broker. The message broker is the central piece of software on your back end where all the clients will connect. It is responsible for persisting those connections with those messaging clients. We'll talk about persistent sessions with those clients if they choose to correspond in a persistent session. We'll talk about message routing from publishers to subscribers. But finally, this needs to be a highly available system. So often it is a clustered, scalable, and reliable solution on your back end that would be set up to support millions of messaging clients. And then finally, we have the messaging clients themselves. They act as the publishers and subscribers through via topics, but with the communication channel through the message broker. So they all share and connect to the same message broker. They may persist message sessions with the message broker and or just be transient, which means there's no tracking of that session with the broker. Next slide. So finally, let's go ahead and talk about some of the operations of MQTT. Sweety?
Thanks, Robert. Wasn't it exciting to know about MQTT and the benefits we get through MQTT from HTTP? So let's look at the operations which Robert already gave a gist to you, and let's deep dive into it. So these are called sub and pub. Pub and sub we call usually in MQTT. Let's look at the subscribe to topic. So we did say subscribing. So mostly in MQTT, we would be using subscribing to topic, publishing to topic, instead of like get, push, those kind of API terms we use in HTTP. So here you see there is a topic and there are different kinds of client connected to the topic. So that means they are subscribing to this topic. So the client 1 can be an Android client. Client 2 can be an iOS client, and client 3 can be a web client. So it doesn't matter. So all of them are clients and they can subscribe to the same topic. The other cool thing is we are going to see the publish to topic. So the publisher can also be a client, and the publisher can publish a message, and the clients who are subscribed to those to the topic will receive those messages. So it doesn't matter that only one client have to receive it, all the clients will receive it because they are all subscribed to that topic. Let's look at an example. So before looking at an example, we should learn about broker. So we say that, okay, I'm subscribing to a topic and I'm publishing to a topic. But how this happens, am I directly subscribing to the topic as a client? And am I directly publishing to the topic as a client? No, there where we have a middleman. That's where we have this MQTT broker. So this MQTT broker will take care of all the connections, your publishing, your topics, everything the MQTT broker will take care. So the client who is subscribing to the topics will ask the MQTT broker, oh, I want to subscribe to the topic. And the MQTT broker will say that, okay, you're good to subscribe to the topic. And the same thing with the client when it's publishing to the topic and say like, okay, you're a valid client and you can publish to the topic. And then I will take that message and asynchronously send to all the clients who are subscribed to the topic. And MQTT broker, which we are using, is AWS IoT Core. There are a couple of other MQTT brokers which are available, like HQ and Mosquito, and other brokers are there, which follows the same pattern. Let's look at an example here. So here is an example where there's a topic called light. Let's look at a simple example. So there's a topic called light. So the client 1, maybe there's an Android client. There's a client 2, like an iOS client, and then there's a web client. All of them are subscribing to this topic called light, saying that any message that comes for this topic, I want to listen to it. And the MQTT broker, which takes this and says that, okay, you're valid clients to subscribe to this topic. So I'm going to take it into account and make sure that you receive those messages. Then publisher is also a client to the MQTT broker. The publisher can be a platform at the backend which is publishing, or an actual device that is publishing, but all of them are considered clients to the MQTT broker. So client which is publishing to the topic light, saying that, hey, the light is on. So the broker takes it and sees who are the clients that are subscribed to this topic light and starts publishing the message on. So all the clients are receiving the message on, and they can act upon it how they want to do it. Let's look at the other cool feature, that is quality of service. I know Robert would have given you again a gist about what is quality of service, but here we are going to learn more about it. Quality of service is a key feature in MQTT protocol. And you can select, there are different levels of quality of service. We are going to see that there's 0, 1, and 2. And you can use those quality of service based on your app and based on your network reliability. Sometimes it manages to retransmission the message and guarantees delivery based on the quality of service you're picking it up. Say, for example, if your network is down at a moment, do you want the client to receive the message again? You can handle it based on the quality of service. It becomes make the network reliable. When you have an unreliable network, it makes the communication a lot easier using this quality of service. Let's look at quality of service 0. So we call this quality of service more like a fire and forget. What happens here is we have the broker, and then we did say publisher is also a client. So that is an MQTT client who's a publisher who's publishing a message in quality of service 0. So the MQTT broker takes this message, publishes it to the client. What happens if there is a network error? The message is not published and it is missed. But the MQTT broker will not care about publishing it again. This is what we call it as quality of services, fire and forget service, because I'm just firing. If you have a network problem, you don't receive it, I wouldn't know about it. But then we have this quality of service 1. So the quality of service 1, we make sure at least once the user or the end clients gets the message. So let's look at how it happens. So the client, which is a publisher, publishes a message in quality of service 1. The message broker, what it does is it sends the message to the end clients who are subscribed to receive this message, and then sends an acknowledgement saying that publish is acknowledged. I have published the message. But if the MQTT client has set up a time, say, for example, I've set up like 2 seconds. In 2 seconds, I don't receive this acknowledgement. I assume that the message has not been sent. So the publisher will publish the message again. So the MQTT broker will again send the message to the end clients. So this is why we say that at least once the end clients will get it, that means they can get it more than once based on, again, the network reliability or the acknowledgement is not sent within the given time of the publisher is expecting to receive it. Then there is another service, which is quality of service 2. So we call this as the safest and slowest because we make sure the messages are delivered only once to the end client. For that, what does it do is the publisher, the MQTT client, publishes the message to the broker with quality of service 2. And the broker, it doesn't publish the message to the end clients, but sends an acknowledgement back saying that I received this message. And the MQTT client and again says, oh, cool. So now I know you have the message with you. That is, the data is there with you. Now go ahead and release it. That's where the MQTT client releases the message and then sends saying that I have released the message and here's acknowledgement. And you do see there is a 4 levels of handshake happening. Anywhere within the time that client or the broker might send a time, right, to get the acknowledgement back from each other. Within that time they don't get, they're again going to keep on requesting it. So that means that, again, it keeps on going until both of them are confirmed that the message is there and ready to be published. And that's why we call this the slowest, but we call also safest because the end client will not receive the same message again and again, but just only once. And if you're using AWS IoT Core, it doesn't support quality of a service 2, it only supports 0 or 1. So based on your network reliability, you can pick 0 or 1. Let's look at what is persistent session. So we learned about quality of service. Let's learn a persistent session. So when a client is trying to subscribe to a message or publish to a message, first it starts to establish a persistent session with a broker. So as I said, if I'm an end client, I'm listening to messages. Maybe you can take me as a mobile client who was listening to messages from whoever's publishing to that. I have to first make a connection. So I send to the MQTT broker with the valid credentials, make a persistent connection. That's where the broker starts to store all the subscriptions of the client. So based on quality of 0 or 1, the client will receive the messages, or the messages are stored. And if they are offline, they will start receiving the messages again. But quality of 0 will not send it. That's why we have not mentioned it here. Let's learn about starting and ending a persistent session. There's a flag called clean session flag, which we can use it. So if you're saying you're setting the clean session flag to true, you're saying, I don't want a persistent connection. What that means is you're telling the broker, don't save any of my subscription information. And if any of my messages are not delivered, don't deliver them, because I'm cool with having a non-persistent connection, because I don't want it to deliver and then when you reconnect again. But then you can also have a persistent connection by setting the flag to false. You're saying, I don't want a clean session. That means store all my subscription information and undeliver the message if they're not delivered. I'm sorry, deliver the message if they're not delivered with the quality of service 1 or 2. To understand the relationship between quality of service 0 and this clean session flag, let's look at this table. So here you see that I said that if a clean session flag is true, it doesn't matter if your quality of service 0 or 1 or 2, after reconnect, your message is not going to be received, because you're saying, I want a clean session. So that means none of your subscription information are going to be stored. But when the clean session flag is false, that's where we can see the difference. So when it's false, you have a quality of service 0. Again, quality of service 0 is what? Fire and forget. So that means it's not going to redeliver the message after you reconnect. But if you have quality of service 1 or 2 and your clean session flag is false, that means I'm saying have a persistent connection, store all my subscription information. That means when you reconnect, your message will be received based on like how many times you have to receive it. Now, the other feature we are going to talk about is the shadow states. What is shadow state? So shadow state messages we call, there are different types of shadow state messages. One is a desired state, and one is the reported state, and one is a delta state. Let's deep dive into what are these states are. First of all, we have to understand what shadow state messages are, right? So shadow state messages are messages used to update or delete a device state. For example, like I have a light device and I want to update the light device to say, turn it on or set a color. So all thus you're saying that I'm updating the shadow state. That's how you say it. Or you can delete the state saying that I don't want to receive any more shadow state update for this light. So there are two sections as a client you will be receiving it. One is called the desired state and one is called the reported state. Here is a desired state you can see as an example where it's saying that as a desired state, I want to turn the power to on and the color to be set to red. Then there is a reported state. Oh, okay. So here's an example that's showing that I'm sending it from the client to set the desired state. And then there is a reported state, which is saying the color is red and the power is on. This means it's saying that the actual device or the actual reported state of the device is color is red and the power is on. And you can see that the light is turned to red and it's on and it's sending the reported state to the client. I consider to this as like a request and response. So you can say like desired state is a request. I'm sending from the mobile client to say that, can you turn on the light? And then it's giving me the reported state. Yes, I turned on the light. And here is your data. With that, let's understand the message payload. You did see that Robert was explaining that's a lightweight and it can work in the low bandwidth. The reason is because a payload cannot exceed more than 125 kilobytes. In AWS, it allows only 125 kilobytes. And if you're using other MQTT brokers, your payload, it allows only a very less. And that's why even in low bandwidth, you can transmit these messages. But what if you have a heavy payload of messages? Say, for example, I have like 10 devices. I have light, I have thermostat, I have like 10 lights, I have like 2 thermostats, I have door locks, all this I have to get them. And this is a heavy payload. So what we can do is you can work with your platform and they can say that, okay, I can send you one payload at a time because that can fit into this 128 kilobytes. That's how we did it. We worked with Robert was from the platform side, was working on it, said that I can send you like one device at a time that you can use to use it. So by this, we had to work on a business logic because I don't know how many devices I'm connected. As a client, I just log in. I don't know how many devices I'm connected. So we have to handle a business logic to say that you have like 20 devices, and then you have to receive all the 20 devices, one payload at a time. And this is how we had, like for example, we have the message payload saying like there's a payload one is coming for device one, there's another payload coming for device two, and there's a third payload coming in. Then we have to have saying that the maximum number of devices you're going to get is 10. So that's how we'll know that, okay, so we are going to get 10 devices. And we also had this num logic where to say that which devices we were missing it. So here you can see that I received the first device, which was num0, another one was num4, and num1. Why is this different order it's coming is, even though the platform sends, the backend sends to the MQTT broker in a specific order, the client doesn't have to receive in the same order. They can receive in different order. This is where it's implicating that the client is receiving this in different order, even though they were sending it from 0 to 1 to 9. The other crucial feature we want to learn about in shadow state messaging is versioning. How do you know that I'm getting the latest data from the MQTT broker? Because right, we can resend the messages. What if you're having a quality of service 1 and 2 and it's keep on resending? How do you know that I got the latest message which was updated? That's where this versioning plays a crucial part. So here it says that I have a reported state that I receive, which is version 3. Then the next one should be version 4. That is, even the reported state next I'm getting should be version 4, or the decide state, that means I'm requesting to turn the light to on, should also be version 4, because the current reported version should be greater or higher. Say, for example, if I'm sending a desired state by setting the version to 2, that means it will ignore it saying there's a version conflict, because it's expecting you to send the latest data. It's assuming that, oh, you're not having the latest data. So you also have to have a business logic to store the latest version and make sure your desired state is higher than the current version. We did talk about delta state, right? So we saw desired, we saw reported state. Desired is like I'm sending a request, reported is giving me the actual state of the device. Then if I want to send a desired state, say, for example, I want to send a request to turn the power to on, the MQTT broker will check in its data, is the reported state off? Only if they are off, it considers this is a valid request and sends the request to the device saying that, okay, turn on your power. If the reported state is already on, and if I am sending it on, nothing happens because it's already on. So this is not even a valid request. So the MQTT broker will take care of handling this delta messages and only sending the data when it is valid. So here you can see, so my power is on. I'm sending the power as on. Right now it's off. It's considered this as a valid state. So it is going to send this power on to the actual device to turn on the power. With this, let's dig deeper into the clients of MQTT, which is Robert is going to take it away.
Okay, thank you, Sweety. So with that great foundation Sweety set to understand what is MQTT, shadow state service, and the messages, let's talk about now how we use that technology from both a mobile client and a gateway device perspective. Next slide. So on the mobile client, we've actually created a component we call the MQTT Manager. It's responsible for handling the connection to the MQTT message broker from the mobile application. It provides the ability for any consumer within our application space to receive messages and to publish messages using different namespaces. Next. Then finally, we have what we call the IoT Manager. It utilizes the MQTT Manager as part of that IoT namespace in order to consume messages that are for IoT device control and notification and publish messages for that space. We have different processes, and Sweety touched on where we are returning multiple packets of payload information for devices. We also have what we call adapters. Adapters are things that are integration points to devices. So for example, If we support Philips Hue or LifeX or our own gateway, we consider those to be adapters. And the mobile client needs to know what available adapters exist for this solution. Also, it needs to discover devices associated with our subscribers and ones that they have already onboarded. And so it returns back a set of packets related to devices it's discovered. It also utilizes the shadow state in the IoT space in order to be able to control through desired state the state of those devices and receive back the reported state of those devices. And then finally, we have this second category where we have the ability to invoke actions. We call them client actions, where a client can actually make a request via MQTT and receive back an asynchronous response outside of usage of the shadow state. Next slide. Well, all important thing is our mobile clients need to be able to first authenticate, which we have our backend system, federated IDP system for exactly that. But as part of that, we get a job. We get an identity token basically back. We need that identity token to be used as the authorization bearer in order to authorize that client to connect to our MQTT broker, to enable it to publish and subscribe messages from that MQTT broker, where the permissions are actually at the finest granularity of the topic level. As we saw, topics can be namespace. They have / delimiters. And as part of that delimitation of that topic, we actually provide identity information as part of the topic. We also have specified a unique MQTT client ID, which is also composed of that same identity information. And that identity information for the client ID and the topics must match the identity information that is inside of the job. Next slide. Yep. So from a client usage perspective, we're going to do device control. We're going to publish to that shadow state topic the message that is the desired state. And we're going to do that publish at QoS level 1 for at least once delivery. And then finally, on the reported state side, we're going to have subscribed to those shadow state topics, and we're going to subscribe and receive messages over QoS 1, which is the notification of the reported state of that device. Slide. So yes, it's unique. We actually do use MQTT from the mobile client perspective. Where it typically has always found its home, though, is on the device side of the equation. And so our device gateways, whether they're our network gateways or our home hubs with our touch screens, all use MQTT for 24/7 pinned-up connections to our message broker. It works both over broadband and cellular for our cellular backup channel for our home security product. And then finally, it uses X509 certificate-based authentication and authorization, as opposed to JOTS from the mobile client. Each device has actually already been given a certificate, device certificate, and that is that certificate that is used at the connection from that device gateway to the broker that bears all the same authorization kind of information. And finally, these gateways, they support many different types of devices. Zigbee is probably our most prevalent. Matter's upcoming standard. We're looking at already porting the SDK to our gateways. But we have Wi-Fi, Bluetooth, many different network protocols we can support. We support a plethora of different types of devices, whether they're different types of sensors, motion, smoke, for example, or door window sensors, door locks, lights that support just on, off, or color, or different levels of brightness, mini thermostats, and garage door types. And we support these all generally the same. We're pretty neutral when it comes to the different types of devices. We have our own data model that we use from both the gateway perspective and the mobile client perspective. So we can transform and translate any third-party manufacturer's data models to our internal data model. That gives us neutrality across ecosystems and device types. Next slide. So a little bit more about that authorization. We do use TLS X509 device certificates, which contain identity information about that device. That information is composed in the client ID, which is also unique for that device. And it's verified against the information in the certificate. If it doesn't match, you cannot connect. Also, the topics are also fine granular topics that have identity information within the topic namespace. And if that identity information does not match and you attempt to publish or subscribe to a topic, you will be disconnected, actually, and we will receive an error that there was a violation attempt. Next slide. All right, so let's pull this all together. And I know this is a bit of a slide, but at the heart of this, we do utilize AWS and serverless technology and AWS IoT Core at the heart of our architecture. On the left side, you can see we have the mobile client, and it has a connection to the MQTT message broker. It has gone through custom authorization, and we have a policy that's been generated that allows that mobile client to connect, publish, subscribe, and receive messages to our IoT platform. The same is true of the gateway, except the gateway uses certificates that have been issued to it and has a network with, let's say, via Zigbee to talk to sensors and light bulbs. And when it connects to the MQTT message broker, it's connecting 24/7, generally speaking, right? And it's using the just-in-time registration process to take a certificate which is pending activation and make that certificate active by verifying that certificate has not been revoked, verifying that that certificate is associated with a subscriber that is allowed, right, this capability, this feature. And finally, we generate a policy that then allows that gateway on behalf of the devices that it's managing to connect, publish, and subscribe to our message broker into the IoT platform. We also support down at the very bottom many adapters for third-party service integrations like Philips Hue, LifeX, Singlid, et cetera, okay? But at the heart and core of everything is our IoT platform, and that is IoT Core in a nutshell. And at the heart of that is the shadow state service, and Sweety mentioned the shadow state messages, right? Well, those messages that are sent and received or published and subscribed are via MQTT. And so anytime, let's say the mobile client up there in that upper left wants to send a control message, a desired state message, right? It sends it via a topic via MQTT, and the shadow state service receives that request and in turn produces potentially a delta state, right? That delta state message would then be forwarded to the gateway that is responsible for handling that, or to a third-party adapter responsible for handling that message. That delta state message then gets translated into an actual device request to hopefully turn that light on, for example, or turn it to red, right? And then once that has successfully been performed, it's the responsibility of the gateway or those third-party adapters to set the reported state based on the action that's been performed. And it does that again by sending a reported state message to the shadow state service. And when that shadow state service changes the state, and the mobile client is subscribed to those topics from the shadow state service, that mobile client receives the latest reported state and can update its UI to reflect that the light is now turned on. So there are many components that make up this architecture. The mobile client, right, based on iOS, Android, or even web clients actually exist today for this. Our gateway, which is an MQTT client, uses an embedded C SDK at its heart and core. MQTT represents the message broker as a highly scalable AWS IoT Core message broker. Shadow State Service represents a separate component within the IoT Core ecosystem that supports that concept of that desired reported state representation. And then we have many message routers. We have the inbound router that routes incoming messages and an outbound router that delivers messages to the appropriate MQTT client. And all of this at the heart and core is serverless and uses Lambdas for a majority of all of the actual business logic that we implement on the back end. Okay. And I believe that is the end of our presentation. So thank you everyone for attending. Here's our Twitter handles. I hope you enjoyed the presentation. If you have any questions, thank you again, and we'll open up to questions.
Thank you so much.
Thanks very much, Sweety and Robert. Really appreciate you taking the time to present to us today. Yeah, so I'm looking both in the the Zoom chat and the Room B Slack channel. So if anyone has any questions, we could entertain those. I'm assuming when you say the mobile client, Robert, I mean, is that primarily the Xfinity Home app?
Well, it's our converged now Xfinity application. So as we're merging a bunch of different mobile applications into one converged Xfinity app. But yes, we also have the Xfinity Home app, and that uses a slightly different communication protocol.
I see. Okay, so someone says that was a nice basic intro, and was wondering if there was any code examples that would have been nice to look at. Are there any public GitHub repositories that that Comcast makes available that has some of their MQTT work for people to look at?
Not Comcast related, but AWS has a lot of examples. They have tried it. So if you go to the AWS IoT Code site, they have a lot of examples where you can use to try it out.
Yeah, actually, it's for reference. Yeah, definitely visit AWS IoT Core and look at the Android and iOS AWS SDKs that are available. And there'll be a lot of examples of how those SDKs can be used to connect to the message broker. We have numerous different types of WebSockets with or without WebSockets. Different forms of authentication authorization mechanisms are supported. And yeah, it's a good starting point.
Okay, so do you have a sense of how many messages that IoT infrastructure that you showed in that diagram? Do you have a sense of how many messages per day Comcast is processing or handling?
Yes, it's many millions of messages per day. I can get an actual real number if I pull up my own dashboard. So we actually we use Datadog on the back end for our dashboards, and so we track all of the publish ins and publish out messages and we can do it on a daily basis. So let me pull up some and answer that question for you. Hold on, I'll get a latest number.
Sounds good.
We track costs that way. We also track different types of errors that may occur. So do it this month. So connections, successful connections that we're getting, and primarily a lot of them from the mobile clients as well, is 10 million connections per day to our MQTT client. And then let's see. We have about probably about 500,000 published outs, which represents the reported state messages that are sent to subscribers. And we have actually less control, because if you think about it, publish ins are people changing the state of their lights. So right now we have 15,000 control requests per day.
Okay. I guess another question that I have is, it seemed like this was primarily on the Xfinity Home side. Are there other ways that Comcast is using MQTT in areas of the company that maybe you wouldn't consider? Or is it primarily with the home?
We are. We have two different forms of API semantics that are supported by the Connected Living Xfinity application, and one of them is REST-based APIs, which is pretty traditional. But the second is we extended that for asynchronous, subscription-based notifications to the mobile application. And so it's not just the IoT space that's using that, but also our internet connectivity space. So for example, our Wi-Fi blaster results processing is done through MQTT.
Okay. All right. Okay, it doesn't seem to be any other questions, but I would encourage people, if they think of things in the next few minutes or throughout the day, to post them to the Room B channel. And Sweety and Robert, is there any final words for everyone before we shut down here?
Thank you so much for attending. Like Matt said, if you have any questions, post in the Slack channel, and I'll make sure Robert answers those questions. But it was great working on this project with Robert. I want to especially say this. He was on the platform side who did a lot of research. Like why we picked even AWS IoT Code is because like he did a research on all other MQTT brokers, and we ended up using IoT Core, and it's very simple. Like they do all the hard work, and from the client side it's very simple. We just get the payloads, process the payloads, and show the UI. So this was a very nice and interesting work we did on the Xfinity app using MQTT.
Thank you, Sweety. Yeah, and likewise, it's fantastic partnering with Sweety and developing a full IoT based solution as we have in the last couple of years.